So what are tetraflexagons? Well, flexagons were developed by Arthur Stone in 1939 and popularized, as you know, by Martin Gardner in his inaugural 1956 Scientific American column. They're made from paper strips, and typically, but not always, they're flat. And the fun thing about flexagons is that they can be manipulated to spring forth hidden sides.
So our question is, should they have a group? Should the set of flexagons, the flexes on the flexagon states form a group? And there's a natural reason why we would think that. There's a natural obvious multiplication, which is do two things in a row. There's associativity is just a given. The natural identity is super difficult. You just don't touch it. And we have inverses. Once you do a flex, you can always do the flex in reverse to get backwards. And the problem child, though, is closure. Because if you've played with the hexaflexagon, you realize that there are sometimes you get to states where you get stuck. And the only thing you can do is go backwards. And this happens a lot with the tetraflexagons and is somewhat obnoxious.
So in thinking about transformations of the Tri Hexaflexagon, Jean Peterson in 1972 wrote a paper called Sneaking Up on a Group. In that paper, she talked about 6 of the transformations of the Tri Hexaflexagon. So if you've looked at the Tri Hexaflexagon, you realize that when you flex 3 times in a row, you get back to where you started, or at least you get back to the face where you started. And so those 3 really form Z3. And then if you also include turning the Tri Hexaflexagon over, then you get the group S3. But if you pay special attention to the Tri Hexaflexagon, like maybe you love it very much and you drew something on it, then when you flex it 3 times, you realize that even though you get back the face you started, it comes back to you in a slightly different orientation. And so in 1997, Hilton, Peterson, and Walsler published the faces of the Tri Hexaflexagon, in which they talk about how the full group of transformations is D18.
So our warm-up example is this very simple case. If you fold this net, so this diagram is the net, if you fold it right along this edge, tuck this corner underneath this guy, and tape, you get a very simple flexagon. It's a tetraflexagon because it's in the shape of a square. It only has 2 ways you can fold it, the way I described, or doing everything in the opposite direction, giving a mirror image flexagon. And it only has 2 states. It can be like the state you originally do it in, or you can flex 1 time and you get a second state. So that tells us that the algebra there has a Z2, and it's crossed with D4. The D4 is this regular symmetries of the square. So what we learned is that, yes, you can have some groups, which are awesome, and that D4 just might not actually be interesting.
But also it might be interesting. For example, if you look at this tetraflexagon net and then fold it in the way that is recommended by Pook, first, you can flex it 4 times in a row and you get back to your starting state. But when you get back to your starting state, if you've decorated it like you decorated your Tri Hexaflexagon, then you'll notice that the starting state comes back to you upside down. So D4 actually is interacting in an interesting way with this flexagon. And in the end, the group that you get is given here. It's D8, semi-direct product Z2, and then cross another Z2. So that Z8 comes from doing the flex 8 times as you need to get back your original starting state right side up.
This next one is a bolt net in Burkhoff and Dumont. And they say that, well, Pook says that this is group Z4, because if you start with it and you do 4 flexes, you'll get back to your initial state. Well, when we were looking at it, we realized that there's actually 2 different types of flexes, which they talk about in their paper. When you have your tetraflexagon in front of you, there's a natural coordinate axis in the middle, and you have 4 quadrants. You can either flex by folding down over the x-axis, which we call an x-flex, or down over the y-axis, which we're calling a y-flex. And you can split those 2. When you split those 2, what you realize is the group you have is actually a Z2 cross a Z2. And then here we recognize we have a semi-direct with D4. Although it's a semi-direct, it's not actually that interesting. It behaves as we would expect. The flip doesn't actually change anything. It's just the identity automorphism. And the rotations, though, when you think about rotating 90 degrees, you switch x and y. So that's all that automorphism does.
Okay, so with this next example, which you call the super snake because of the long net, We are showing you the detailed structure diagram, so that shows you some of the states that are labeled, and then also the X and Y flexes that get you from one state to another. Notice that if you start at the state F, E, H, G, you can do 2 Y flexes in a row, so they must be different from each other. That state is a special state where you can actually do 2 Ys in a row. And so we've labeled them differently, Y and then Y hat. So the group that we found is 4 copies of Z2 and then semi-direct with D4. So you might wonder how we got 4 copies of Z2. One comes from the X, one comes from the Y, one comes from the Y hat, and then remember how Julie just explained to you what happens when you semi-direct with D4. The X and Y get switched under the rotation, and so when you rotate the Y hat, it becomes an X hat. And that's the 4th copy.
The next ring we want to talk about is, or the next net we want to talk about is the ring net. This is in Birkhoff and Dumont. They list a number of structure diagrams that you can get from the ring net. So the next 2 examples are 2 of the very interesting foldings from there.
So this one, in a sense, is like the super snake. Well, in a couple of senses. One, it has that crossroads point, so you can do 2 Y flexes in a row, and you can also do 2 X flexes in a row if you see that. So you might not be surprised that the group structure is 4 copies of Z2 semi-direct with D4. But it's a little bit different, even though it looks like the exact same ring structure, because in this case, the flip switches the role of X1 and X2, and Y1 and Y2.
So as we've been looking at these, we've been looking at the structure diagrams and seeing what qualities might indicate that there is a group. You notice one of the earlier ones wasn't just a closed cycle, and this one is particularly bad. Everything emanates from this point, and he's very badly behaved. Closure is just, seems like a lost cause. But what we realized after playing with this for way too long is that it lives inside of the Z8 structure diagram that you looked at earlier. And if we make some identifications in the diagram and then make the same identifications in the algebra, we find that there's a group with these 4 generators, these relations, that actually matches the flexes. And we haven't introduced the D4 symmetries yet into this example, but this was really surprising. It told us that somehow these tetraflexagons are much more intimately connected to each other than we originally thought, because these were from different nets completely. So that was really shocking. So that's where we're going in the future. How can we learn about one flexagon from another flexagon? Do the structure diagrams actually encode all of the algebraic information that we want? Some other directions that are being explored, I have an undergraduate working on, given a specific net, how can you determine all of the foldings beyond exhaustion? How do you actually know you have them all? And then, are these groups even the right algebraic tool? I mean, they're awesome and they work for the things we're looking at, but maybe we're missing something or there's a bigger object at play. So for your own edification, because I know you're fascinated, here's the bibliography. You can look up all these awesome things, such as Weihart's Flex Mexagon. If you haven't done that, you should. It's good. And flex away. In your packet, you will get, in your gift bag, you'll get flexagons from us and trading cards that tell you how to make all of these flexagons.
Thank you.